So we're going to do about 4 lessons on applications. The very first one, this one, you're going to be given the equation. After that, you're going to have to develop the equation. Okay, so we'll focus on that in the next lesson. But in this one, we're going to focus how we use a given equation. But it's important, it will be useful to think about the different pieces of the equation given the question. And what every part means. So that's what we're going to start with even in this lesson, is analyzing these equations, understanding what the different parts are. But we're going to be focusing on how to use them for this lesson. Okay. So this is the equation of an exponential function, application kind of question. It looks a little different from the ones that we were just graphing, because the ones we were just graphing was just something like this, 2 to the x. But you'll notice that there is an exponent, and t is like our x. So our x is in the exponent for these questions. Okay? So we're going to analyze what each part in this equation means. And it won't always be capital A that we use. I'm going to pick different letters. The letter that you use doesn't matter. We tend to use particular letters for particular kinds of questions. You'll see what I mean when we get there, because the letter matches what the question is talking about. But you can choose whatever you want in those cases. Again, we usually use letters that are different from numbers. Okay, so this capital A is the final amount. The other capital A that has a subscript of a 0, and you may run across this on the radio, or if you take math after high school, they often call it A naught, and that's a big British thing as well. So naught is sometimes how they refer to 0 or none. So it's A naught. But it means like A at times 0. A at 0 is kind of what it means. So it is a common notation for what we will call the initial amount. If you don't have a calculator out, by the way, you're going to need it. So you can get it out when we start using it. Most of you probably have it out, but we're going to be using our calculator a fair bit for this, so keep that in mind. Okay, and then B, which is in the brackets, is the base, or the multiplier. So it's how is the question, the application, the relation, how is it growing or decaying? So we called these increasing and decreasing. But when we do applications, when we talk about functions, that's the language we tend to use when we were talking about the graphs in the last lesson. When we do applications, we tend to call it growth and decay, exponential growth and exponential decay. Okay, but it means the same thing. Is it getting bigger or is it getting smaller over time? T is fairly obvious. It's the amount of time that's passed. N is a bit of a tricky one. It is the growth or decay period. And that word period kind of means what it meant in trig functions, but not exactly. So how long it until the growth or decay happens. As is often the case, these will probably make a little bit more sense when we actually get into examples, and we're going to talk about each of these in the context of the examples. this is going to be all the more important that you understand what each of those variables means when you have to make the equation. Because you're going to read the question, it's going to give you the numbers. You have to figure out where to put the numbers. Okay, that's our next lesson. But, again, I'm not going to ask you to define these things, but you're going to need to know, generally speaking, what each of those letters, what it is, what it means in the context of these questions. Good so far? All right. Let's take a look at the first example. Population of rabbits on an island. These questions can often be ridiculous, like a lot of questions can be in math classes. But we'll go with it. Some of them are very realistic. The idea behind this is very realistic, but real life is a lot messier than we want to get into when we're just learning about a new topic. If you were to actually look at a real life situation of a population of rabbits, there's a lot more going on than just the exponential growth involved. We'll talk about this again in a second. Population of rabbits on an island can be modeled by the equation below. You can see it there. T is time in months, and capital P is the population of rabbits. How many rabbits, right? It's not written up there, but hopefully that's kind of obvious in this case. So question A says, explain each of the values in the given equation. And as I say, in the next lesson, you're not going to be given the equation, you're going to be given those values as part of the question. And you're going to have to figure out where to put them in the equation. That's why it's important for us to analyze these now when they're given, because that's what we're going to have to do next. So when I look at, I've got the 100, it says the values, just the numbers. I got 100, I got a 2, and I got a 4. BEDMAS says this is not 100 times 2. BEDMAS says exponents happen before multiplying. So this is not 200. This is 2 raised to an exponent and then times 100 at the end. Okay, so be careful of that. You cannot combine those parts. So what are those? Well, let's do it from left to right. What is the 100? Where is it? Well, it's the A naught. It's the initial amount. So in this case, I'm not just going to say it's the initial amount. Initial amount of what? Rabbits. So 100 is the initial number of rabbits. Or population of rabbits. Or the current, sometimes we think about time starting now. So how many rabbits are there now? And like this is where time kind of starts, right? But using the word initial could be a good idea if a question like this ever came up on a test. What about the 2? Aaron, what do you think? 2 is the base. What does it mean to have a 2 in there in the context of this question? This is kind of tricky. I'm not sure I would expect anybody to be able to figure this out. But if you have insights, as always, you can share them. Yeah, no, that's right. It is the base. What does the base represent, though? It represents how it's growing. So if it's a 2, how is it growing? It is increasing. The population of rabbits is increasing. And 2 is the multiplier. So I'm taking the population and I'm multiplying it by 2. And then after a certain amount of time, I'm multiplying it by 2 again. And then after a certain amount of time, I'm multiplying it by 2 again. So in this case, 2 means the number of rabbits is being multiplied by 2 or is doubling. Okay, that's going to be an important word, doubling. So that's the way it's growing. Finally, the 4. If we go back up to our explanation up here, 4 is your n. N is how long until the growth or decay happens. So it says t is time in months. That means the 4 is also in months. And the 4 means it doubles every 4 months. So the n can be a tricky one when you have to set up the equation yourself. But it means you're doubling every 4 months. In order to use the equation, we don't necessarily need to know all of that, but it's going to help us a lot when we have to make up the equations ourselves. Everybody got this okay? Question B. How many rabbits will there be in 2 years? So once you have your equation developed, we're going to do 2 things. There's 2 variables left in this equation, 2 unknowns or 2 variables. The t and the p. We're going to learn how to sub in for t and find p, and we're also going to learn how to sub in for p and find t. So we're going to learn how to solve for both. Okay? So you could narrow these down. Once you've got every question after today is going to, the part A is going to say make an equation, and part B and C are going to be use your equation. So once you've made your equation, now it's your job, am I subbing in for t or am I subbing in for p? So this, I think in a lot of cases is going to be obvious. That won't be the hard part, but it is something that you can actively think about. How many rabbits will there be in 2 years? So it's giving you time. It's giving you t. So what is my t? Is it 2? Some of you are shaking your head. No, why? What is it? Why 24 months? Yeah, very good. So hopefully there's going to be a few little conversions that you have to do. You need to know how many hours are in a day, how many months are in a year, how many days are in a week. You're going to need to know a little bit of that kind of stuff to do these little mini conversions now and then. Why do we have to convert? Because the question says t is time in months, but then it's telling us 2 years. So we have to take the 2, convert it into number of months. As I said, hopefully that's fairly straightforward. It is 2 times 12 because there are 12 months in a year. So we are going to use the equation at t equals 24. And I'm going to make a little note here. You don't have to write this down when you're doing your own work. 24 is 2 years in months. I would say this is the easy one. Subbing in for t is the easier of the 2 types of questions that we're going to do. So p equals, oh, and by the way, remember how I said we don't always use a? So I use p. Why did I use p? Because it stands for population. We're talking about a population of rabbits. You could have used the capital R for rabbit, or you could use a. If you want to use a, that's fine. It really doesn't matter. So again, we're given the equation, so I'm just writing it down. 2, but t is 24 divided by 4. And we're just punching this into our calculator. Now, what is 24 divided by 4? You can do that in your head, can't you? It's 6. So just to save myself some time, that's what I would do. If you can, sometimes you might not be able to, it'll be too big, or it'll be messy or something like that. But if you can, why not? Otherwise, 24 divided by 4, you're punching it in like that. You got to know how to use a calculator. Again, as we said before, some of you might need to use brackets. Since mine actually has an exponent section, I could just type it into that part. But if yours has a little hat, you might need to use brackets to make sure that the whole 24 divided by 4 is in the exponent. Or you can just write 6. Is maybe easier. Did everybody else do that? I would recommend trying it on your calculator. It's not super hard, but make sure you can get it. 6,400. And we usually end these with a therefore statement. Therefore, there will be 6,400 rabbits. 6,400 in 2 years? Holy cow. So in real life, nothing works by a formula, right? Like rabbits have a season where they have babies, and over the winter they tend not to, or at least they have fewer babies, because you don't want to raise babies in the winter. So over the course of the year, it's not like every 4 months exactly it's doubling, but averaged over the year or averaged over time, population growth does follow this kind of growth pattern. And why would that make sense? Well, 2 rabbits have a litter of 4, and then some time passes, they grow up, and now you've got actually 6 rabbits all having litters. And they all have litters of 4 or 6 or whatever, right? Or even if it's just 2 or 3. And then they all grow up, and now you got like 10, 20 rabbits, and they all have litters. So every time there's litters happening, there's more rabbits that are having litters. So that's why it's kind of exponential growth, and it makes sense that it would double. So, and the reason why often you'll see these questions are like on an isolated island. Well, because rabbits have predators, and so they don't all get to grow up and have babies. They get eaten by coyotes and that kind of thing, right? So in real life, it would be a lot more complicated. You'd have to, like, what's the food source like? An island could only hold so many rabbits before there's not enough food to go around for all of them. What kinds of predators are there? Are there hawks getting these rabbits? Are there coyotes? Are there wolves? Like, you know, there's lots of other details going on. So we're just looking at if all those things went away, how would the population grow? Okay? Okay, straightforward enough, right? Subbing in for t and solving for p, or solving for the final amount, is fairly straightforward. It's just calculator work. Next one's a little bit trickier. Next one says, if the population keeps growing at this rate, and again, a lot of the questions don't say that just because, you know, we're not going to repeat it every single time, but it's always assumed that something doesn't happen, like the island doesn't get flooded in a hurricane and all the rabbits are wiped out, right? Assuming that the island, the food source can sustain this many rabbits, assuming that predators don't move in, assuming all of these things, if the population keeps growing at this rate for a long time, how long would it take until there's over 3 million rabbits? It's a lot of rabbits, right? So let's see how long it will take. So in this case, it's giving us the population, and that was 3,276,800. It's giving us the population, and we're solving for time. So I sub in p on the other side, where the p in the equation was. And write down the rest of the question. And now I have an exponential equation to solve. Well, that's what we were just doing. Now these ones have a little bit of a twist to them. So we do have to, and as applications always are, they can be a little bit harder than the other kinds of questions that are set up for you to practice. These ones can be a bit messier. The numbers can be a lot bigger. Or sometimes they're going to be decimals. There's going to be all kinds of things that kind of come up that make them a little bit harder. But that's what we're going to practice over the next several days. First thing we have to do, all that work that we did solving exponential equations, by the way, that's all going to come into play. Like where you're trying to rewrite with the same base, that is what we're going to do. But before we do that, we got to manage this 100 because it's in the way. Remember when I said that was one of the things in that lesson was there can't be any other junk. You got to have just the exponent part, just the power. 2 to the something equals 2 to the something. Not 2 to the something equals 100 times 2 to the something. No. We can't do that. So the first thing you're always going to do when you're solving these, the nice thing is it is a step-by-step process, is divide by 100. Or whatever that initial amount is. You're going to do that every single time. And that works out to, let's see, 3, 2, 7, 6, 8. 32,768. Okay, so you're probably going to do that on your calculator. Very often you're going to get a decimal there. Equals 2 to the t over 4. Now watch carefully. This is where all that work that we were doing before comes into play, but the numbers are a lot bigger. 2 to the something equals 2 to the t over 4. This is like if it was an x there, right? If this was 2 to the x, the 4 doesn't want to disappear. This is what we were doing before. Okay, but instead this is 2 to the t over 4. Don't worry about the over 4 part. We're going to deal with that afterwards. So this is where we're going to get out our calculator. And you're just going to have to start trying things. Anybody have a wild guess where you want to start? Do you know what it is already? Okay, I don't want if you know. I'm curious what your guess would be. Like I'm not going to start at 2 to the 5. I know what that is. Okay, 2 to the 11th. We've talked about 2 to the 10. We've seen questions with 2 to the 9. They're not quite as big as 32,000, so that's a good guess. That's still pretty low. What are you going to go to next? Oh, let's try 2 to the 22. Whoa, way too big. We talked about this before. Exponential growth is very fast. So you may not want to jump up that high. I'm doing this on purpose, like making mistakes on purpose to kind of give you an idea of how far you want to go. Cadence, what do you think?
15.
Try 15. So we tried 11. It was way too small. 15 is bang on. So 11 was way too small, and we only had to creep up a few more steps, right? So from 11, maybe you try 13 or 14, and you just got to keep trying things until you get it. That is how this works. So 2 to the 15 equals t over 4. Therefore, 15 equals t over 4. Now what do I do with the over 4 part? I multiply both sides by 4. And so t equals 60. 15 times 4 is 60. It'll take 60 months, which happens to be exactly 5 years. Not very long for there to be 3 million rabbits. But populations like rabbits or other rodents can grow very fast if left unchecked. Any questions? We're going to do several more if we have time. And they are a little bit different, so it's important that we look at the different examples. Any questions? We're going to add that next step eventually where you have to make the equation, but otherwise all the questions look a lot like this. Okay? It's going to say, it's going to give you a length of time and you solve for the final amount, then it's going to give you the final amount and you solve for the time. All right, let's look at this next one. The value of a baseball card can be modeled by the equation below where t is time in years and value is in dollars. How much will the card be worth in 50 years? How long until the card is worth $2,080? Now, what's different about this one is it doesn't have, the exponent doesn't have like an over 4. There's no n. Okay, it's not asking us to define the numbers, by the way, but we still know 3 is the initial amount, so that's how much the baseball card cost at the beginning, or how much it's worth today, right? 1.08 is the growth period. So that's very different from 2, which was doubling. This one's growing a lot more slowly. It's still growing. We'll talk about this more another time. But 1.08 is still growth, but it's slow, so it's got a decimal in it, and that makes this question a little bit messier, a little bit different. Okay, so we're going to see what that looks like, and like I say, it's just t, there is no n value. It means that the growth period is every year. Okay, so A, how much will the card be worth in 50 years? So that's an amount of time. That's at t equals 50. And it's asking us how much is it worth, so what's the value? So I'm solving for v. Anybody have a guess? It can be hard to estimate these things. 50 years doesn't seem like that long. Does it? So again, I just type it in. Wow. 140 bucks. That's pretty good. It was only $3 50 years later. Worth over $100. Some things can grow like that, like baseball cards, if it's a rare one or an important one or something like that. Okay, what do we round to? It doesn't say in the question. Why would you say that? Just because that's the way we usually do? Yeah, so that's a good guess, but there's something about this question. Probably 2 because it's money, right? So 2 decimal places is to the nearest cent, which is how banks do it and how the real world kind of works. Now, a question might say round to the nearest dollar. Like, I don't know if somebody would quibble over buying this baseball card and paying you 70 cents. Like, you might not really do that, but our rule in this course will be if it's about money, you round to 2 decimal places. So V equals 140.70. Therefore, it will be worth $140.70. Add your dollar sign in there because that's like your units. And we'll move on to B. How long until the card is worth $2,080? So again, like I said, it gave us time. We solved for value. Now it's giving us value. We solve for time. How long is asking us to solve for time, right? Better make sure I can fit this in. So at value equals 2080. What's our first step? Always? Abrar? Divide it by 3, right? We got to move that 3 over. Very good. So divide by 3 on both sides. And that gives me kind of a messy number. 2080 divided by 3. I don't want the fraction. I want that. So 693.33. And this is like I say, when we get into applications, it can get a bit messy. So here's what we're going to do. Get out our calculator. Remember, like if you look at this and you're stuck because the numbers are not friendly, and you're like, I don't remember what to do now. Well, when we're solving exponential equations, it's always, we have to write with the same base. Right? I have to figure out what to put in that box. So I just start trying things. Now we did 50 years before, and 50 years gave us $140. This is $2,000. So it's more than 50 years. Do you understand what I'm saying? You'll save yourself a bit of time on a test if you make some smart guesses. So what do you think? 100 years? If you already know the answer, don't tell me. I don't want to know the answer. I want everybody to like have a chance about guessing. Or do you have a question?
What did you do to 693 instead of 2000?
Do what to?
Like, what did you, like, when you were finding the exponent, what
Yep.
did you do to 693?
Yeah, that's what we're going to do.
Oh, okay, no, like I said.
Yeah. Oh, well, I see what you're saying. I gotcha. I understand why you're asking that. You're asking that because I said it grows up to 2,080. But that's with the times 3. So when we got the 140 as well, that was the final amount. So you're right, we're going to make it equal to 693. But I'm comparing the end values. So that's why I said 2,000. So I'm going to try doubling it. You got to start somewhere. Hey, that's not bad. But it is too high. Okay? So, I don't know. Just start trying things. Go back to, how about 90? So 90 is, oh wait, no, sorry. I'm looking at the wrong thing now. Now I am making a mistake that you were talking about, Cadence. I don't want it to be 2,000. I want it to be 693. So I'm still way over. 90 is still way over. So we're going to keep going down. How about 80? Too low. So I'm jumping by tens and it's making a pretty big difference, right? So how about 80? Whoops. How about 80? I'll go halfway, 85. Whoa, that's really close. Now watch what I'm going to do here. Off to the side, I'm going to write that down. 1.08 to the 85 equals 693.46. It's not exact, but it's really close. But I'm going to check the one above and below, just to be sure. Okay? You don't have to write it down when you do this, but you do need to do this. Because in some cases, you might get really close, but there's actually something that's closer. So 1.08 to the 84 is further. So that's no good. And what about to the 86? Is too big. So 85 is correct. Do you understand? I'm also writing it down so I can show on paper that this is a guess and check. Right? So sometimes, like some years, I've even kind of written down all my guesses. Like we tried 100, but it was way too big. Then we tried 90, but it was way too big. Then we tried 80, but it was too small. Then we hit 85 and got kind of lucky. Right? So I'm right, but I think you have to at least, you don't have to write them down, but you want to try, if you think you have the number, you want to try the one just below and just above it as well. Okay? So the number is 85. Whoops. Wrong color. $85. And I'm going to change this equal sign to an approximate sign because it's not exactly true. It's very close though. So therefore, t equals 85. And therefore, it will take 85 years. In 50 years, we got to $140. In just 35 more years, it's worth over $2,000. Eventually, it would cap out. In real life, it wouldn't go on forever and be worth millions and billions and trillions. But we're not worried about that for math class. We're just looking at what the numbers tell us. Does that make sense? Okay. Got a couple more still. Any questions? Yes? Why don't you wait till we're done? 15 minutes, we're at break. Okay, the amount of nitrogen-16. This is a very specific kind of question. Amount of nitrogen-16 remaining after an amount of time has passed can be determined using the equation below, where T is time in seconds and M, capital M, is the mass in grams in this case. Sometimes it's grams, sometimes it's milligrams. This one's grams. So this is a half-life question. We'll see these in a couple more lessons down the road. Notice that my multiplier is a fraction. It's smaller than 1. Our first example was 2. The next was 1.08. This is 0.5. So this is decay. This is getting smaller every time. And that is how radioactive material behaves in the real world. It's called half-life. Radioactive material decays over time. That's how they do like carbon dating, and they don't just use carbon anymore, they use other materials as well, but how they figure out how old very old things are, like dinosaurs, that kind of stuff. They use this idea of radioactive decay and half-lives. So it's, again, a very important particular application that we're doing here. Is a real thing that people all over the planet do all the time. Okay, explain each of the values in the given equation. We're going to do this one a little bit faster. Hopefully we're getting used to this by now. What's the 8,000? The initial amount. Initial amount of the nitrogen-16. I don't know how many of you have taken chemistry and learned about this, but like you all know what nitrogen is. You've heard of that. It's an element. 16 is the isotope of the element that this is, and it means it has 16 more protons or neutrons or something like that. I don't know the specifics. Someday I should figure that out, but that's just what it means. So it's a particular type of nitrogen that's radioactive. So it decays over time. Regular nitrogen doesn't, right? Okay, so 8,000 is the initial amount, so 8,000 grams. What is the half? It means we're talking about half-life. It means the amount is being cut in half. And what does the 7 mean? Means it is cut in half. So the decay or the multiplier, let's see, this is time in seconds. It is cut in half every 7 seconds. And take a look at B and C. B gives us the amount of seconds. We're solving for how much, the final amount. And C gives us the final amount, and we're going to solve for time. How long? How many seconds? So the same kinds of questions we just did in the other two. You might want to use 0.5 instead of a half. That's fine to change that. So 8,000 bracket 0.5 to the 28 over 7, that's 4. So 500. We started at 8,000. 28 seconds later, but every 7 seconds, watch this folks, this is kind of interesting. Every 7 seconds it's cut in half. 28 seconds is 4 intervals of 7 seconds. So it's being cut in half 4 times. Right? Does that make sense? So 8,000 cut in half is 4,000. Cut in half again is 2,000. Cut in half again is 1,000. Cut in half again is 500. And there's your 4 half-lives. So it actually makes sense. And you can, if you were to write this out, you can actually see how the numbers in half-life work. Therefore, there will be 500 grams left. C is giving us the mass, which is what, 125? So 125 equals 8,000. So what do? Divide both sides by 8,000. Now 1 over 64, if you're good with your numbers, that number might actually be useful. I'll let you think about that. I'm going to use the decimal. So this is 0.015625 equals 0.5 to the t over 7. So again, and I'm going to flip sides here. Don't be confused about this. 0.5 to the t over 7 has to be 0.5 to the something. And I have to figure out what that something is. Anybody have a guess at what we should start at? Random guess. What would be your random guess? We're not doing anything with the fraction yet. We're going to do that after. We're just picking a number that I'm going to punch into the calculator and try. 0.5 to the 3? So I'm trying to get that decimal. 0.125 is not right. I'm going to go up bigger. How about 50? Way too small. That went into scientific notation. How about half of 50? 25. Still way too big. 15? Still way too big. 10? Still way too big. Briar, you might have been even closer. How about 5? So I'm getting closer now. That kind of looks like the number I have here. How about 6? And see how it was that 1 over 64? So that might have actually been a better way to do it. But there I got the number. So it's to the 6. Therefore, t over 7 equals 6. Multiply both sides by 7. T equals 42. Oops. Any questions about that one? So we got one more to go. We don't really have time to fit it in, so I think I'm going to stop now. But what I am going to do is I'm going to show you the answer and just briefly talk about it. There we go. So what is the value of the car in 5 years? So it gives us the formula. Again, this one's about a car value of a new car determined by the equation given. The 32,000 is the initial cost of the car, or initial value of the car. Again, this number is smaller than 0, so the value of the car is decreasing over time. Doesn't that make sense? Isn't that what happens to most cars, except for collector cars, right? Their value drops every year. You drive it, sell it in 5 years or 10 years, it's used. You don't get your $32,000 back, right? We all know how that works. So how much is the car worth after 5 years? And so I punched in 5. This will be on the classroom if you want to copy it down later. You could try it yourself and see if you get it right. Just under $10,000. So it lost 2/3 of its value. More than that in just 5 years. That's accurate. This is kind of how things work. Don't try to copy it down. You won't have time. I can leave it up and you can copy it down after. Just listen. Then it says, how long until the car is only worth $600? So again, that's when the value is 600. I plugged 600 in on the other side, divided by 2,000, worked my way down, and you can see my list over on the side of where I found my numbers. So I got to 15, 16, 17, and I'm trying to get 0.01875, and I got 0.1877, right? So I got fairly close at 16. So you buy a car for $32,000, 16 years later, the thing's only worth a few hundred. Again, that's pretty accurate, depending on always other details, how much you drove it, where in the world you live, because in Canada with the salt on the roads, it wears cars down faster, right? There are definitely other variables involved, but that can definitely be accurate. A 15 to 20-year-old car is only going to be worth a few $100s. Okay, any questions on that one? So you can take a look at that. To me, these are the trickier ones where it's not an exact answer and you kind of have to do that little list off to the side to try to get to, as close as you can.